that as before, the slides are already online. You can follow the talk via looking at the slides. And our today's speaker is Ayan Mukhopadhyay from Indian Institute of Technology, Madras. And he will talk about SL2R lattices and networks as information mirrors and decoders. Ayan, welcome to HelloTube, and please.
Yeah, thanks everybody, and hello everybody. Thanks for the organizers for giving me the opportunity to give this talk, and thanks to everybody for being here. So I'll be talking about my upcoming paper, which is, there's a technical title here, SL2R lattices and networks as information processors. But there is also a simpler title, which is it's basically talks about a model for an old black hole. It tries to see how you can model an old black hole as an information processor. So is my audio coming out correct? Is it perfect? Am I audible? Okay, thank you. So, so my talk will be based on this upcoming paper with my present graduate students, Tanay and Hariram, who are at IIT Madras, and Alex. He worked with me when we were in Vienna, and when I was in Vienna, and now he's at Stony Brook. And this also mentions some earlier work that we did before. It's published last year, and this is with Lata Joshi, who is now actually in Innsbruck. She has moved to quantum information completely, and Alex again. The figures in these slides has been made by Tanay, so thanks to him. And I also want to show you some nice picture here. I mean, during this lockdown, this has been my nice constant companion, because we had a very draconian lockdown here, and for a month at least I was not even allowed to get out of home at all. So this has been quite a nice inspiration to do this to work on this paper. Right, I have some issue with moving slides. Okay, so the plan of the talk is as follows. So I will have an introduction and motivation to what we are doing, and then we will present the model of a black hole. And any model of a black hole should first address the question, what are the microstates? Whether we can capture the microstates of a black hole, and what we will see surprisingly, that our model can also tell us that the arrow of time will emerge. And then we will try to see how a black hole, how our model behaves phenomenologically. So to understand whether our model is a credible model of a black hole, we will try to shock our model and verify the results. And then we will talk about the Hayden-Preskill protocol of the black hole, that how this is one of the information tasks that we should verify whether our model captures rightly. And then I will talk a general picture of a fragmented holography, and I will conclude with an outlook. So I start with the first part. So the first parts will be a bit longer, and the later parts will be shorter. So this is the introduction. So the title of this slide I have taken from a song by a band from US. It's an indie rock band called Dr. Dog. And the title of the song is That Old Black Hole. In one of my later slides, I'm going to actually give some of the lyrics of this song in the right context. So what is an old black hole? An old black hole is a black hole that has passed its page time. So the page time is a time when half of the Hawking quanta has been emitted out of the black hole. And of course, it's for an astrophysical black hole, this is a hopeless time scale. It's if you have a sun-sized black hole, it will be 10 to the power 67 years. So it is much, much, much larger than the age of the universe, or perhaps even the universe can ever live. So it is kind of hopeless. But what is so interesting about it is that theoretically, it is the most puzzling thing, because for various reasons. So if you start with an initial, a typical initial state that describes a black hole, and we assume that the evolution is unitary, then the reduced density matrix of the Hawking radiation can be maximally mixed only at page time, and then entanglement entropy of the Hawking radiation has to go down. And this is essentially due to Page's theorem. So Page's theorem tells us that if we take a typical state, and we have we partition the state into two halves, not necessarily two halves. We've simply bipartition the system, and we ask when the reduced density matrix will be maximally mixed, and it is maximally mixed when we trace over exactly half of the degrees of freedom. So this is very well known. This is called Page's theorem, and this simply implies that after the page time, after half of the Hawking quanta has been emitted for a typical initial state, the entanglement entropy of the Hawking radiation has to go down, which means the information of how the black hole was formed will start coming out. But this is very hard to reconcile with Hawking's original computation, because in his original computation, this radiation is thermal, and there is no, and the time evolution is not unitary. So the entanglement entropy will simply grow and then saturate instead of coming down. So this is how it. So we need to somehow make sure that we need to understand how Hawking's computation can be still correct, and we can still have some curve like this. But then there are also other kind of paradoxes. This is not the only paradox that we are that has been discussed in literature. There has been cloning and also AMPS paradoxes. So I will discuss this cloning paradox, which is very simple. It's simply that you have Alice and Bob, as usual, and Bob decides to jump into the black hole first, and Alice decides to wait. And then after Bob jumps in, there is a Hawking quanta emitted, and Alice gets this quanta, and she measures the state of the quanta. But then there is an EPR pair, because Hawking quanta is always there's an EPR pair involved, and Bob has the other one which stays inside the black hole, which falls inside the black hole. And then after Alice decodes this quanta, she jumps inside the black hole and compares with Bob, and she sees that, so then they verify that they have cloned a qubit. But this is not possible if you have unitary evolution in quantum mechanics, and and therefore something has to give in. And so what Hayden and Harlow suggested in 2013 is that one way to resolve it is that, and also actually they also suggested in the context of the AMPS paradox. So, and essentially the AMPS paradox shows there's some kind of tension between the various kind of assumptions that goes into black hole complementarity, including that we have a smooth horizon, we have equivalence principle, and the evolution is unitary, and also then there are these various quantum information identities involving in subadditivity of entanglement entropy. So showing all of these are intentions. All of the postulates of black hole complementarity cannot hold. And one of the ways to kind of avoid all these paradoxes was what Harlow and Hayden said, that if you want to actually process the information of the black hole interior in the Hawking radiation, it will actually take a computational time which scales exponentially with the entropy of the black hole at page time. So while the black hole kind of completely evaporates away in polynomial time, so this particular cloning paradox thought experiment cannot even be carried out, because Alice will take such a long time to decode the quanta that the black hole would have evaporated away by then. So in a very recent paper, Kim, Tang, and Preskill has actually revisited many of these earlier kind of arguments, and they have made it more solid. And they have shown that they have actually made a very nice computational model of it, and they have argued that this should work out if the post-time Hawking radiation is pseudo-random. And there is a quantum version of pseudo-randomness that they have precisely defined in the paper, and they have showed exactly how this Hayden-Preskill resolution is actually a very very reasonable. So I would just ask you to please interrupt me, and because I'll be very happy to be interrupted, because otherwise it's because I can't see you, so I will be happy to get some feedback. And so please do interrupt me in between. So then it turns out that one can try to model the black hole as some kind of a quantum eraser channel. So the old black hole turns out to be some kind of very interesting information processor. So first of all, they're supposed to be very fast scramblers that comes out from this OTOC computations, which were first done by Stanford and Schenker. So what it basically means is that if you have an infalling qubit, it is rapidly mixed with the interior degrees of freedom of the black hole in a very rapidly, as rapidly it can happen in nature. Now, in a way to understand the black hole as how a black hole actually works, one can actually make a nice computational model. It's not a physical model, but it's some kind of a quantum circuit-like model. So, basically, one can think of it like a quantum eraser. So here is an infalling qubit into the black hole, which is psi A. And this is the state of the black hole at page time, which involves the black hole interior and the Hawking quanta that has been emitted out. And these are in some state beta. It's in a pure state beta. Now, after the quanta falls inside the black hole, there's a unitary operator that acts on the black hole interior degrees of freedom and this quanta. There is some unitary operator, and then it gets maximally scrambled. And the black hole interior, of course, nobody can access. The observer outside cannot access. But then there is also the Hawking radiation that comes out, the late radiation. And then the early radiation and late radiation together forms a Hilbert space on which one can actually put a decoder, which is again a unitary gate, and get this quanta out. So of course, this operator V will depend on U. And of course, whether the black hole is a fast scrambler or not will depend on what kind of architecture of this unitary operator it is. And if you put in a typical unitary operator here, if you choose it with a Haar measure, it is already good enough to have a maximal capacity and will be a fast scrambler. So what Hayden and Preskill were argued that if you believe in this kind of quantum eraser kind of model, then the old black hole is actually an information mirror also. And any infalling information will leak out in this time, which is of the order of the RS log RS, where RS is a Schwarzschild horizon radius at the infall time. And this also should be the scrambling time. This is because in the same time that the black hole, this bit gets scrambled, you should be able to operate this V to get the information out.
Tim, can I ask you something?
Yes.
On the previous slide, like, is only the old black hole a fast scrambler, or because you're saying the old black hole is a fast scrambler, but isn't it true also for a young black hole?
Good question. Yeah, I guess it should be also a fast scrambler, but the information mirroring, I think, yeah, it is a statement of an old black hole. Is about an old black hole.
Maybe that's because only during the old black hole phase you can extract some information or decode the information from the black hole, but the dynamic of the black hole, whether it's a fast scrambler, I kind of expect that it should hold even when it's a young black hole. But I might be wrong. I'm not
sure.
Yeah,
it's a good question. No, I really don't know the answer, but I don't know the correct answer to this question. But because I'm not very familiar with this computational models, which requires a lot of quantum information inside. But as far as I understand, yeah, that this information mirror, this kind of gate, it's kind of, this is a good model only after, I think yeah, okay. So I think it has to do with whether you have enough degrees of freedom here to operate so that you can get this information out. You have to have enough number of degrees of freedom on both sides, I guess. So you and
yes,
me should,
I see.
yeah,
I see.
should
Okay.
work on equal, yeah.
Okay, thank you.
Thank you. So Kitaev and Yoshida in 2017 had a very nice computational model of the Hayden-Preskill protocol. And they said how you can construct the V for a given U. But it's only a computational model. So our motivation is somehow to make it physical. And essentially we were kind of inspired from this recent progress where this page curve has been explicitly computed for Hawking radiation via ADS-CFT. And in this case, the entanglement entropy has been computed of the Hawking radiation has been computed using something called the quantum extremal surface, which is essentially the Ryu-Takanagi surface with appropriate quantum corrections. And this has been actually computed in the semi-classical geometry, so which actually the same geometry which Hawking would like to use in his computation. So it is in a two-dimensional JT gravity, and the matter is in the form of a conformal field theory, which is coupled to this gravity. And so the geometry can be trusted, but what happens is that this quantum extremal surface, it acquires the first order phase transition at page time. And this reproduces the page curve. If you compute the surface area of the quantum extremal surface, it will reproduce this behavior. So one question that we can ask is whether we can construct a simple phenomenological model for the black hole as an information processor in which we can explicitly demonstrate all these features together, that is scrambling, information mirroring, and page curve. And also see how the Hayden-Preskill protocol should actually work. I mean, the idea is to gain some kind of insight into the mechanisms of these processes and how a black hole is supposed to work. So first, there are some disclaimers, of course, that we don't want to be a quantitatively exact model because that is hopeless, because quantum gravity is extremely hard and also do it in real time and it's also hard. So we are not trying to be quantitatively exact here, and we don't want to reproduce a black hole entropy here or derive our model from first principles, although we want to construct it based on some kind of non-perturbative dynamics, non-perturbative quantum gravity dynamics that we already know. Now, even in terms of these phenomenological features, our model likely needs some improvements in terms of how fast it scrambles and things like that. And we will discuss some generalities later. But even with such reduced ambition, it is still a challenging task to come up with some model that describes black hole macrostates, that walks and talks like a black hole, and especially captures some mechanism for all these processes. So we will see why it is really challenging in course of time. So now we come to the model. So essentially our model is inspired from this fragmentation instability of the near extremal horizon. This has been actually discussed by Brill in 1992, but has been physically interpreted much more clearly in this paper by Maldacena, Michelson, and Strominger. So essentially it is an instanton-like solution. So you take an extremal black hole horizon with certain charge, and this is actually an electric charge. It can fragment into two throats, which has charges Q1 and Q2. So that Q1 plus Q2 is Q, of course. Now, what can be shown is that the instanton moduli space, the metric on instanton moduli space diverges when, or is singular when these fragmented throats come very close together. So you have abundant low energy modes at the boundaries of this instanton moduli space, where two or more throats are separated by sub-Planckian distance. So basically these gapless modes are essentially kind of gravitational hair that leaves on this throat, on the tip of the throat. And then there are these fragmented throats. So our model is somewhat kind of inspired from this. We don't try to derive it. It's simply something like this. We just put it by hand. So we have this, we have some kind of a lattice of this ADS2 black holes. And the lattice has the same dimensionality as the horizon. So if you have a 4-dimensional black hole, the lattice will be 2-dimensional. And then of course, each of this ADS2 throat will have an extra radial direction. So it's a lattice of these throats. And then there are this mobile hair. This mobile hair essentially are the charges corresponding to the isometries of the unfragmented horizon. So this is basically the tip of the throat. They have SL2R charges. So our gravitational mobile here are essentially these gravitational charges QI, which are the SL2R charges of the unfragmented. And these can move around the lattice. So these are the ingredients. So the ingredients basically are these two categories. So one is an NADs2 throat lattice, which has the same dimensionality as a black hole horizon. And each of them has a separate SL2R symmetry because ADS2 has SL2R symmetry. So corresponding to the isometries, they will have these SL2R gravitational charges, each one of these throats. But then there is also a pure gravitational hair, which can be mobile. And these are the mobile SL2R charges. And these are the SL2R symmetries of the unfragmented or what was the unfragmented throat. So this is essentially we have these two ingredients. And what we cannot miss here is essentially that we cannot, so we should have the same symmetry which we started with. So the symmetry of the full model has to be the symmetry of the unfragmented throat, but each of the throats will have independent SL2R symmetry. So this has to be broken to a diagonal SL2R of the unfragmented horizon, because there's overall one geometry which connects every through. Of course, we don't see this geometry explicitly in the effective model. And then there is we should also have an overall conserved energy. So now I would like to quote some of the lyrics of this song, which I mentioned, that old black hole. So especially these two lines. So I don't expect you to believe me, but everything is all right. So essentially, at this point, we have no guidance how to come up with some interactions. And the key point is we have to somehow couple the lattice SL2R charges, the throats, the isometries of the throats, with this mobile gravitational hair. And we do not know what coupling to use, but you have to simply somehow believe me right now that this is a right kind of coupling that works. And if you think of any other kind of coupling, it may not work. So our justification will be phenomenology, essentially. So this is a kind of model. This is exactly how a model looks. If you think of a chain, so think of the horizon is just a circle. So you have a three-dimensional black hole now, and this is so we have a periodic chain, and then these are the nearest neighbor kind of interactions that we have. So this M is the ADM mass, or basically the holographic EM tensor of the ith throat of the black hole. And this equation is essentially a diffusion equation. It doesn't look, so to see it explicitly, you have to take the continuum limit. Then this becomes a Laplacian. And this Qi prime is not constant, but one thing you can note is that if you look into this equation, it's basically linear in this air charges. If you sum over all i's, then this right-hand side of this equation vanishes. If I sum over all the lattice sides. Therefore, sum over I Qi prime is conserved. And therefore, there is a strong monopole component here, which is homogeneous. And what you can show that, okay, and because sum over I Qi prime is conserved, so it will be a constant. So it will be, so there is a strong constant monopole component, and then there is a diffusion term when you take the continuum limit. So this is almost like a diffusion equation. And then this is essentially a Klein-Gordon equation with specific kind of sources. So each of this throat is described by Jacques-Teitelbaum gravity with a dilaton and appropriate matter EM tensor, which I'm coming to. And this model has a conserved energy, which is very simple, which you can simply see from these two equations that we just described. And so it's simply easy to see that this total energy is conserved. So the energy is simply a sum of the masses of the ADS2 throats and the energy in the hair. And this is the kinetic energy in the hair, and this is essentially the potential energy, which is in the continuum limit becomes grad Q squared. Okay. So now I will give a brief description of each NADS2 throat, what it is and how we describe it. So each NADS2 throat is described, as I said before, by Jacques-Teitelbaum gravity coupled to some matter. So the matter we don't need explicitly for reasons that we will see. The equations of motion of this gravity is rather simple. So if you look at the dilaton equation of motion, it's simply r plus 2 by s squared is equal to 0. And it simply means that the metric is always locally ADS2. And then if I compute the G mu equation of motion, I get that the total energy momentum tensor is conserved. So there's a contribution from matter, and this is essentially the contribution from the dilaton. And actually this equation satisfies the Bianchi identity. So these are not 3 equations, but actually 1 equation. Essentially the content of the equation is as follows, that if you put in some bulk matter, it reparameterizes time in the boundary up to an SL2R. So that's the content of this equation, as we'll see. Now the solution of this equation is rather, of this thing turned out to be rather simple. So this metric, which I wrote down, is locally ADS2. So it has constant which is scalar. And m of u is an arbitrary function. So m of u is actually the ADM mass, and it turns out is the right kind of variable which evolves in time. But alternatively, we can also think, instead of m of u, a different kind of variable, which is a time reparameterization variable, t of u, which I'm defining now. And essentially, it is the boundary limit of a bulk diffeomorphism, which is also called a uniformization map. So what happens is that if you make this particular diffeomorphism, the bulk diffeomorphism, you can map this metric to the vacuum solution, which mass equal to 0. So if I make this particular diffeomorphism, and as you see that if I take the limit, so r is equal to 0 maps to rho is equal to 0, the boundary maps to the boundary, of course, and then the t of the time reparameterization is actually the same at the boundary, is simply t of u also at the boundary. And now if I do this, so m of u can be expressed in terms of t of u, and the expression is rather remarkable. So m of u simply is a Schwarzian of this t of u. So essentially, it has to be the case because there is SL2R's isometry of the ADS2. So this is reflected in this formula that because of the isometry, m of u should not change if I do a SL2R transformation of t of u. And this is the definition of the Schwarzian. So now the solution for the dilaton and the EM tensor is also turns out to be also very simple. So the solution for the dilaton is simply 2 by r. Actually, this factor of 2 is because of a Dirichlet boundary condition, which is simply we choose. It can be anything else. So it's simply set by an appropriate Dirichlet boundary condition. And then the matter that is inside, we can take it to be null. And we will see why in our case we need only to consider null matter. So we have this particular null matter where only the UU component is non-zero and given by some f of u. And then this equation, this complicated equation, actually reduces to rather something simple. And the content of this equation is nothing but this simple thing that m prime of u is f of u. But m of u is nothing but the Schwarzian of the time reparameterization variable, t of u. So the content of this equation is rather simple, that matter reparameterizes time up to an of SL2R. So this is the content of the equation of the equation of motion for a dilaton. So let us take a very simple example. So the simplest example is when f of u is 0. So in that case, the Schwarzian has to be a constant. And the most general solution up to SL2R is that t of u is nothing but tan hyperbolic of pi u by beta. And this beta essentially determines the mass, because the mass should also be a constant because it's a Schwarzian derivative of t of u, and it's 4 pi squared by beta squared. Now the physical importance of beta is that if I do Euclidean rotation, then this becomes tan, and tan has the periodicity beta. So it has the Euclidean time has a periodicity beta. So this black hole with this particular constant mass is basically a thermal state with temperature beta inverse. But generically, T of U can be arbitrary. It will not take form like this. And essentially, it belongs to this coset space diff by SL2R. So this is exactly what happens in the SYK model also. In the low energy limit, essentially all states are given by a time reparameterization variable, where U is physical time and T is the time of the vacuum. So if you want to compute any kind of non-trivial correlation function in this non-trivial state, all you have to do is to do a conformal transformation on the vacuum correlation functions with this particular reparameterization T of U. And SL2R transformations will keep the correlation functions invariant. So this is the this is the physical meaning of it. So we can also define the SL2R charges, and SL2R charges are defined as follows. So so instead of talking of T of U, it's better to talk of something else called tau of U. So T of U is the map of the physical time to the time of the vacuum, the physical time of the state and to the time of the vacuum. But now we can define tau of U, which is a map of the physical time to the time of the black hole with this particular temperature. And this, so we do a redefinition of this way. And if I rewrite the SL2R charges in terms of tau of U, it looks like this. But actually, if you write everything in terms of T of U, then this beta disappears. So beta is a fictitious variable. It simply sets a reference state for us, which helps us to do some simulations better. So a finite beta is simply good for simulation. So beta can be chosen arbitrarily, and we set it to 2 pi. So now how to simulate the system? So first of all, we should note that if I take time derivatives of these SL2R charges, they turn out to be exactly something proportional to the Schwarzian, the time derivative of Schwarzian. But the Schwarzian is related to the mass. Setting beta is equal to 2 pi, we get these identities that one can work out. And also tau prime, one can eliminate tau prime in favor of some linear combinations of these 3 variables. And this is exactly what we get. So now we note that this particular equation for the Schwarzian was a 4th order equation, because Schwarzian has 3 time derivatives and Schwarzian prime will have 4 time derivatives. But instead of talking of a 4th order equation, we can break it up into 4 first order equation. And this is exactly what we do. This is actually our protocol that we developed in the last paper in 2019. So what we do is simply use these 3 identities and these 4 identities. And then we initialize Q0, Q plus, Q minus, these SL2R charges, and also tau of U. And then we simply use these 4 equations to evolve them in time. And this actually can also work with arbitrary matter. So it not only with null matter, but with any arbitrary matter, but it becomes a bit more complicated. But you can look into our papers. You can simulate any time-dependent solution of JT gravity with matter using our protocol. So now let us come back to our model. In our model, you see that our equation is like this. So every throat, the mass of every throat evolves like this. So it simply means that essentially this particular term is essentially the inter-throat coupling will determine how much of null matter energy goes in and out of each throat. And essentially this is the formula. So now on the right hand side of this f of u, you can simply substitute this particular couplings, these particular terms, and then you can actually forget about the matter sector completely, and you can directly use our equations to evolve them. So you have to simply initialize this 3 SL2R charges, tau I of u, and also this hairs, the hair degrees of freedom, and then this will give you a unique deterministic evolution. Okay, so one should also note that this gravitational hair satisfies source discrete Klein-Gordon equations. This is what it is. This gravitational hair is simply a linear equation, and if the SL2R charges are all homogeneous, then actually the gravitational hair completely decouples from the SL2R charges and is freely propagating over the black hole. So this is the cartoon again, which I wanted. So I just want to make some comments. So what we are doing here is that we are assuming the large n limit in each throat simultaneously. So we can utilize semi-classical JT gravity approximation in each of them. But the hair QI should, in principle, these Roman QIs should be treated quantum mechanically in principle. But we can simplify our life and say that they are in a coherent state. So we can also treat them classically to a very good approximation. And what we will see is that we can do some Hayden-Preskill protocol even with this kind of classical approximation. The page curve can also be computed in our model because we can also couple our model to to CFTs. Each of the JT gravities can be coupled to a bulk conformal field theory. And then one can also redo the computations of the papers that I mentioned. And we can certainly learn something new, but in this, so far, we should only focus on the mechanism of information processing. And so we will relegate this page curve to a future work and a future talk, maybe. Now, I don't have time here, but I just want to point out that our model has many remarkable resemblances with this color glass condenser theory, which describes saturated gluons in PQCD. Particularly, these ADS2 throats can be thought of as chromo-electromagnetic flux tubes, which are essentially describing this the small X gluons. But the analogy actually runs much, much deeper. So I don't have time to kind of say more about it. You can see our paper for more details. Okay, so here I have kind of described the model. I would like to take some questions. If there is any question about the model, please ask me.
Since you also mentioned the SYK, it looks to me like that your model is somehow similar to putting SYKs in a two-dimensional lattice. Like if you consider each of the black holes as an SYK dot.
Exactly. Exactly. Yeah, I will have more to say about this actually. Indeed. I mean, yeah, one should be able to also do something with SYK dots also. And it actually has some lot of resemblances with many of the models Senthil, Sachdev, and recently have discussed in the context of reproducing the linear interresistivity in strange metals. So the one very common feature that this model has with those models is that I think there is this overall SL2, particularly the model Sachdev has described, there's an overall SL2 asymmetry. Anyway, so this is just some side remarks that I will. Okay. Yeah, thanks for the question. Okay, so I will talk about microstates now. So any quantum black hole model, the first thing is that you have to understand what are the microstates. And so what should be the microstates after all? There should be some solutions which are time independent. So they should have time independent lattice charges, these fancy QIs. The throats, ADS2 throats will have constant SL2Rs, and they will also have constant masses because the mass is simply the Casimir of the charges. Okay, so this is something identity I forgot to mention, that the Schwarzian turns out to be the Casimir of the SL2R charges. Okay, the Hare charges QI can have two parts. One part which is locked with the black hole interior, that is simply correlated with this lattice charges, or they could be simply decoupled and freely propagating on the lattice without affecting any of the throats or any of these charges QI. So, it can be linear sum of these two. And then in this particular solution, these two energies, the energies that the total mass of all the ADS throats combined and the energy in the Hare charges should be separately conserved in these solutions. So this is what are microstate solutions. And so it turns out that the solutions are of this form. So all the fancy Qs, all the SL2R charges of the throats, one of the components have to be aligned and equal, whereas the other components can be random. So let us see how it works. Why is this the case? So if you look into our equations, then you can see that if all the charges are homogeneous, then this part vanishes, and this corresponding QI prime can be anything, and still the right-hand side will be 0. So then, yeah, and so in these particular things, because they're homogeneous, this particular component, this will be source-free, and they will satisfy some free Spine-Gordon equations. On the other hand, there can be other possibility that these QI primes vanish, But then to be consistent with this equation, they have to be locked in with this. So with the SL2R charges. So essentially the hair can be either locked in with the black hole interior so that the second equation, the right answer of the second equation vanishes, or they can have these particular components, but then it should be exactly this component where we align with the homogeneous part of the SL2R charges. So I think there is some typos here. So there should be plus minus on this side, and there should be also plus minus. This is a site independent vector. And here there can be also some K0 component, which I forgot to write here. But anyway, so as I mentioned, these particular terms will satisfy a homogeneous, will be completely decoupled, and because these particular source terms are homogeneous, they will be zero, and they will satisfy decoupled Klein-Gordon equations. And sum over I qi is equal to 0, and sum over I qi prime is equal to 0, which is consistent with this. We simply put in this so that we don't do double counting, because there is alpha u plus 1 plus k0 term, which I forgot to write, of course. So for absence of double counting, I simply do it like this. So what we should note here that we have completely exhausted the SL2R symmetry. There's one global SL2R symmetry, which we have exhausted to align the homogeneous components of this QI zeros. I think this should be a fancy QI zeros in the zero. So essentially what I mean is that I say that the homogeneous parts are aligned in a zero direction. And this is where I've already exhausted the only available SL2R symmetry that I have. And then we can also initialize these tau I zeros to be anything. It doesn't matter. And the positivity of the energy will require that the mass of each is positive definite. Is non-negative. And we also require that tau I prime, and tau I double prime will be continuous, because our equations are fourth order in taus. So we need these three variables to be continuous, and that puts some additional restrictions. And these restrictions can be of two kinds, either this or this. So I don't want to elaborate more, but it turns out that if I put this restriction, it turns out that all the tau I primes has to be non-negative. And if I put this restriction, all the tau I primes has to be non-positive. So it means that either all the arrows of time are pointing towards future, or all of them are pointing towards past. So there's a uniform arrow of time will emerge in our model, and we simply choose this possibility because we want to simulate the model in future and not in the past. Okay, the Hare-Church solutions will have these three components, which I mentioned. One is this components which are locked with the black hole, interior charges. So again, there's a plus minus here, and here the zero components are zero. So it is these components which are locked with the black hole, or locked with the black hole interior, which I call QI locked. And there's a QI monopole term, which I mentioned before, which is simply alpha u. And it's, as I mentioned many times, this sum over I QI prime is conserved in our model. So this alpha is something is a primordial variable of the black hole, and it never changes, even if you shock the black hole. The alpha is always a constant. Now there is also this radiation part, which involves these oscillating charges which satisfy the Klein-Gordon equations, which I showed here. So this is this particular part, which is only in the zero direction. And this is what I called the radiation component of the hair. Because they decouple from the black hole, essentially. And they live only on the throat of the unfragmented horizon. So now what we expect is that this particular part, which lives with the throat, which actually will escape to the asymptotic geometry, and which interacts with asymptotic geometry. So this part will not remain with the microstate. So although the microstate can support this kind of hair, the hair will somehow decay, and it will not remain with the microstate. But the monopole cannot be radiated away by gravitational radiation, so it will stay with the black hole. So essentially, in the hairy microstate solutions, we can then split the energy in the hair into three parts. And one part is simply the potential energy of the part that is locked with the black hole. The other is this energy in the monopole term, and the final part is the energy in the radiation. So this is certainly positive definite. if lambda is positive, and this is also positive definite if lambda is positive, where this is actually a random component, which can be either positive or negative, but on average, the total energy will be positive if lambda is greater than 0. So we choose this lambda to be greater than 0. So if I talk about hairless microstates, then it will have a fixed total mass, a fixed Q, which is like the order parameter. And then there is this monopole charge alpha. And fixing all this, we can then allocate the masses at each side and the Qi plus minus component randomly subject to these inequalities. The inequalities are these inequalities which were discussed to have these things continuous. And we can also add here on top. So each microstate solution can also support this radiation component, which freely propagates over the lattice without affecting it. Okay, so now I come to the next part, is that why we should believe in our model. So what we have to do is to see if our model actually walks and talks like a black hole. And so Dr. Dog actually asked you to trust our model. So I quoted his lyrics, but now we should verify if everything is actually all right. He said everything is all right, but we should actually see if everything is all right, then these three things must hold. And what are these three things? The first is that if shock waves fall into one or more of our throats in the microstate solution, so if something goes inside our black hole, then the full system must relax after some time to another microstate solution, with or without hair. So otherwise it is not really like a black hole. So if you throw something inside a black hole, the black hole must relax, and it should go from one microstate to another microstate. Then the injected energy in the shocks should almost completely go into increasing the total black hole mass. So it should almost like 99% or something go into just increasing the black hole mass, and only a very tiny fraction, if at all, will go into the hair. Now, during the transition time, so we have one overall conserved energy, but what we require is something much more interesting, is that so when the black hole goes from one microstate to another microstate, these two energies, the total black hole mass and the hair energy, would be separately conserved. Obviously, they will not be conserved when the shocks are going in, because the shocks will increase the mass. Actually, most of it will go into increasing the mass. So the masses will jump, the total mass will jump. But when there is no shock or nothing is simply evolving on its own, then these two things will be separately conserved to a very good approximation, because that's how a normal black hole behaves. So it turns out that if we have this monopole charge, which is positive, then all these three things work out. So now what I mean by shocks here is that you have these extra inputs, so like delta function injections of energy into the masses. And essentially it means that inside each of the throats, there will also be an additional matter involving some energy that follows null geodesics and falls inside the ingoing null geodesics. They follow ingoing null geodesics and fall inside each of these throats. Okay, so this is what happens if you do a single shock. And what we study is a 5-side periodic chain model. So you see it behaves in the right way. So essentially the total energy is conserved. Of course, it's not conserved when you are shocking, because you're injecting energy. The total energy jumps. But you see, the jump is essentially the jump in the total mass. If you look into the hair energy, it doesn't change at all. And obviously something is happening. There's a lot of non-trivial dynamics happening here, which we don't see. And it's actually washed out in the scale. So there are very, very small oscillations here, because the total energy is conserved, but individually these are not conserved. There are very, very tiny oscillations which eventually die down as it. And actually you can show that the ratio of oscillations to total mass goes to 0 in the continuum limit. So it is actually, so the oscillations don't go to 0 in the continuum limit, but what goes to 0 is a ratio of the oscillations to the total mass. And so this is what is happening inside. So if I look into the 0 component of the SL2 charges, because I start in a microstate solution, they're all the same. And after I shock, so this is, you see, it is the first site which has been shocked because it is this particular site which is where the SL2R charge is jumping. On the other cases, it is continuous. So our model is a causal model, of course. So you see that all these QI0 charges again converge to another's value, which is very crucial because that's exactly what must happen if the system has to relax to another microstate. Now you might ask why it is a zero component again which is homogeneous. And the answer is simply that it's a monopole charge, that alpha, which is always aligned in a zero direction and which is conserved even in presence of shocks. That actually tells you that the final SL2R frame in which everything will be aligned will again be the zero direction. So this is exactly what I've written here. And this is how the plus and minus components happen. So what you see is that they also relax to some values. So you go from one microstate to another, of course, but the final values are almost completely uncorrelated with the initial values. So anything can happen, whatever is up and down. I mean, so you can actually you have to simulate a lot of this kind of initial conditions to see that. So essentially dynamics can be claimed to be pseudo-random, and this is going to be inherited by the Hawking radiation that comes out from the throats. And this is actually necessary for the Hayden-Preskill, Harlow-Hayden scenario, which I mentioned earlier. And the other thing is that, which I don't plot here, is that the final microstate actually has has this kind of decoupled QI oscillations. So a very, very tiny, although the total energy in the hair is conserved, some of the potential energy is unlocked, and this potential energy of the which is unlocked, and it goes into some kind of decoupled oscillations, which is here, the QI. Okay, so now it is time to discuss the Hayden-Preskill protocol. And again, I will just simply show you the diagram. It's kind of mimics a quantum circuit-like diagram. So what happens here that Alice, she decides to kind of make some information completely disappear. So what she does is that she encodes the information into shocks, and she shocks her model, and essentially all the information is encoded in terms of the time ordering and where the shock's going. And so this is how so this is classical information, of course. At this level, it's still classical. And what she does is that she shocks this, she throws all the shocks inside these throats. And then we have this particular initial microstate. So it has this particular components of the hair, the radiation component, the monopole component, and the part locked in with them. And once the shocks go in, there is a non-trivial dynamics that happens. There is a lot of mixing. But then eventually the system settles down to a final microstate, and we have decoupled radiation. Now, the Hayden-Preskill protocol cannot access the black hole interior. You cannot access this part, which has this monopole term, the charges of the throats, and also this part which is locked in or with the charges. So you cannot access this, but you can only act your decoding on the decoupled hair, and you get back this information of the shocks, which means that you can decode this secret information. So you can decode where she's shocked, and also what was the time ordering of the shocks. So this is exactly another way to see it, that we have Alice throwing in some secret message, and this non-trivial dynamics, then this hair oscillations kind of decouples from this interior, and Bob applies his decoder and decodes this message. So how does the decoding work is that if you look into this, the radiation component, it follows a Klein-Gordon equation. So it will have normal modes. And if I look into a 5-side chain, it has 2 positive frequency normal modes. So, and we assume also for simplicity that there is no radiation component to begin with. And this is something that I already said is a realistic assumption, because it's very likely that it will decay to the asymptotic geometry. Okay, so then what happens is that you want to decode it, and what you do is that you have these two positive frequency normal modes, So you do the Fourier transform after the decoupling. You do the Fourier transform, and you simply look at the phases of these two particular modes, and you compute the phase differences. So the phase differences of these normal mode oscillations is what does the decoding. And the shocks can have different kind of energies, but they should not be too large or too small. So then our thing actually works. So let's see. So this is how, sorry?
Excuse me for interrupting. Like, why is it reasonable to assume that you don't have initial radiation if you're working with an old black hole?
Well, the radiation will be there, but it is simply gone to the asymptotic part. It's not Hawking radiation, by the way. It is simply this hair. This is classical hair oscillations, which is essentially living in the asymptotic throw, right? But we have somehow cut it out, right? We are not actually including the asymptotic geometry, like the flat space part or the asymptotic ADS part of the geometry. We are only considering the near horizon geometry. So these particular hair oscillations cannot simply live there. It will be somehow decoying because it's interacting with the asymptotic part. But it actually doesn't, okay. So it actually doesn't matter, because suppose if it is still there, so then if you remember the Hayden-Preskill protocol is supposed to work on the full radiation subspace, right? The early plus late. It will be just more complicated. But what we are trying to understand, the decoding protocol, what happens if it is, say, this part is not there, whether it scales so the fundamental question is here, that whether the complexity of the decoding protocol scales with the complexity of the interior or just with the complexity of the inputs. And what we find is it scales only with the complexity of the inputs and nothing to do with the interior. You can start with any arbitrary microstate. It doesn't change. It doesn't depend on the complexity of this particular dynamics.
Okay, I see.
So here is how decoding a single shock will go in. So suppose this is a five-side model, and here this particular site has been shocked, and this is what we write here as the phase differences between these two normal mode frequencies. So you see there is some kind of symmetry, and this symmetry is actually exact within our numerical error, within our numerical accuracy. And you see that these two have the same phase differences, and these two also have the same phase differences. So essentially from this symmetry, you can understand where you have shocked. So you might say it is very trivial. Of course, there has to be symmetry, but of course not, because it is a very non-trivial result, because we start from very highly asymmetric random initial conditions. This happens for any arbitrary initial condition, however asymmetric it is. And also not all features of this radiation component, which is decoupling from the black hole interior, will have this symmetry. For example, the amplitudes of these normal modes will not have this symmetry. So only the phase differences have this symmetry. So only certain features will have this interesting symmetry. So now you could ask what happens if there are two shocks instead of one. And then it turns out that you have to look into the maximum and minimum of these phase differences. And so you can see that this is maximum and this is minimum, and these are somewhere in between. And noting where the maximum minimum is, you can know where the positions of the shocks are. Now, if they are nearest neighbors, then it turns out the minimum phase difference was the one that was shocked first. And again, this is a feature that is independent of what initial conditions you start with. And that is why it is so remarkable. On the other hand, if these two positions, which is maximum and minimum, are not nearest neighbors, these are the two things that has been shocked. These are still the right places where the shock went in. But now the minimum phase difference site was shocked later if these two sites are not nearest neighbors. So that pretty much covers everything. But however, it is not very easy to generalize this kind of protocol to multiple number of sites and or multiple shocks. First of all, you have to make sure that all the shocks are going inside before the system can relax. Because once the system relaxes, it loses, you cannot expect this to work anymore. So you have to give all the shocks within the relaxation time. And we do not know actually, I mean, in principle, of course, if you have more sites, you have more normal modes, you can also look into the phase differences across sites. But we do not have an explicit protocol yet for, like with arbitrary number of sites and arbitrary number of shocks. But we expect that something like this should hold generically. and this will scale with the complexity of the inputs and not with the black hole microstate. Now you can ask what happens if you throw in qubits instead of classical bits. Then of course we have to go back to the description of the hair as a quantum system, rather as an open quantum system, which is interacting with this lattice of ADS2 black holes. So this is a path of ADS2 black holes, which we have to then take into account. And so yeah, it's something interesting. And it will also be interesting to understand the Hawking radiation in this context and see how the Hawking radiation interacts with this decoupled hair oscillations and carries information away to the asymptotic geometry. And all of this could be interesting. But I think the basic point is clear because Bob can actually also directly access this hair oscillations in principle. And because it is something that is not part of the black hole interior. It's completely decoupled from the black hole interior. Okay, so I think I have to essentially have a very short section. So can I get 5 more minutes?
Yes, sure.
Okay, thanks. So I will then discuss a bit more kind of generalizations of our model, which, so we can call this paradigm as a fragmented holography. So what essentially it means that normally when we talk about holography, we mean that there is some unfragmented spacetime. So if you have a d-dimensional quantum field theory, the dual is something like a d+1 dimensional classical geometry, and it's a whole geometry. But instead what we are doing here, we are, instead of talking of one continuous geometry, we are having some lattice of ADS2 geometries. And and actually it can be part of normal holography because a non-supersymmetric black hole horizon is supposed to have this fragmentation instability. It has been discussed also by Oguri and Fafa in the swampland context. What can be more general than what we discussed? So first of all, why we should consider more general possibilities. So first of all, if you ask me, is my model a good scrambler, a fast scrambler? I don't know yet because we have not been able to compute yet what is the entropy in our model. It's a very hard problem because it involves a lot of combinatorics. So we plan to do it some other time. But because we do not know what's the entropy of the model, I do not know whether my model is a fast scrambler. But what is likely to happen that if you can now that these ADS2 black holes are kind of disconnected from each other, somehow if you are able to connect them by wormholes, then signal can go faster because signal can go faster through the interior rather than from the on the lattice. So which is basically the boundary. So then you expect that it can probably become faster if you somehow do this. So what we propose is one simple example is that you have a 3-site model and each of these sites have these SL2 charges. And what you can do is that you can now take this as ADS2 throat and basically make a pant out of it, a pair of a pant. So these boundaries are geodesics, are null geodesics. And then you have 2 end-of-the-world branes, which carries, essentially they're geodesics carrying some SL2 charges. Again, QA1 plus QB1 will be this SL2 charge, the original SL2 charge. And then what you can do, you can glue them. You can glue these adjacent pants together. And this will have a proper causal structure. So so of course the causal structure will be self-consistent, but you can still simulate it because it's possible to simulate such things. And so this construction is very similar to replica wormhole, but not quite. So you might wonder what exactly such a construction might mean from the point of view of field theory. And we suggest there can be a possible dual to this particular construction. And this actually looks something like this. So if you go back to this paper of Kurkulu-Mandasena, they suggested that if you take an SYK dot and you can project this state of the SYK dot to some spin state, spin half a collection of spins. So you can go and read the paper, how exactly it can be done. And what you can do, you can bipartition these spins, exactly like you are bipartitioning the geometry into 2 pants. And then what you can do, you can take these nearest neighbors and entangle them maximally in whatever ways. So then you have basically what you're producing here is some kind of a matrix product state like network of SYK spin states. And actually this particular thing exactly has same number of parameters as the network, wormhole network I showed earlier. And it is possible that we can actually also simulate such things in a future work. So we are looking forward to that. So anyway, whether these two things are duals of each other or not, they're independently, they're very interesting and should be understood. So I will just end with some conclusions and outlook. So the first conclusion is essentially that we have constructed a phenomenological model of an old black hole. It is merely phenomenological because it captures just some qualitative features, like you have this feature of relaxation. If you shock it, it goes to another microstate, and the energy is completely absorbed into total mass, and the mass remains constant, almost constant, and all as this thing is within transition and everything that they want to have for a normal black hole. And also we have a very good model for understanding how it acts like an information mirror and also as a scrambler. So, and basically our model has pseudo-random dynamics, and we actually are copying these two information in two parts like an EPR pair, although we have a classical analog of it. It goes, it basically also in part of the microstate, internal, interior, and also it goes into the decoupled air oscillations, which we can use to decode what the infalling information. So, this works out, but we have not answered some very basic questions, like can we reproduce the entropy? Can we reproduce, and how does it, and more general things that we discussed, like the wormhole network, and how does this particular wormhole architecture can affect thermodynamics? So also we can ask whether it is good for anything else. So can it be good for understanding strange metals, given this kind of nice kind of resemblance to kind of SL2 lattice, some SYK lattice models considered by Sachdev and many others before, like Senthil, Balance, to understand strange metals. And there's also some good reason to believe that some kind of version of a model can capture instant on liquid aqueously. So there are these various kind of possible generalization, and also fragmented holography in some form can can be part of the usual non-supersymmetric holographic physics at thermal scales, because we know that any horizon, any non-supersymmetric horizon, after all, will have this kind of fragmentation instability. And the other interesting thing is that each of these JT gravity is dual to like an ensemble of matrix, random matrices, an ensemble of random matrices. So it's interesting, it might be that this kind of a picture will have its own universal predictions. It's just a thought, so which we have to explore in the future. Anyway, so this is probably just a beginning of understanding this kind of questions. And so, I mean, although it's just a model, it's not a quantitative model of a black hole, we can still learn a lot from such models. This is exactly what I wanted to ask. This is exactly what my message is. Okay, so that ends my talk. I just end with a picture of this endangered species. It's a black buck in our IIT Madras campus. So if you come to our campus, you will see this, one of these creatures. And thank you for your attention.
Okay, let's thank Ayan for his very nice and interesting talk. Is there any question or comment? Questions? Okay, Ayan, let me ask a question myself. My question is, it seems that in your derivation, the decoupling of Q rad, can you hear me?
Yes, yes.
Oh, the decoupling of Q radiation in your notation QI rad from the final microstate is crucial. I would like to know whether this is some kind of assumption that you have put on top of the Hayden-Preskill protocol, or it has been already assumed there.
I think it's an essential feature for the Hayden-Preskill protocol to work in the first place, because in principle, the decoder cannot access the black hole interior, and you should have a clear separation between what is interior and what is exterior. Now, when something is happening in between, so essentially this hair is living on the surface, so they're all mixed together, so you cannot really make a separation. But at the end of the day, after the full system is relaxing to a microstate, you can make this separation. And And that allows the Hayden-Preskill protocol to be defined in the first place.
Right. Thanks. Okay. Any other question? Before closing our today talk, let me also mention that we will have some special news for students coming soon. So in order to get more information about them, please stay tuned. And let's thank again for our today's speaker, Ayan. Thank you very much.
Thank you very much. Thank you very much for having me.
Thanks.
Have a nice evening.
Oh, thanks. See you all next week. Okay.
Yes.
Bye.
Bye.